consensus. What time does everybody have? Time to rock? All right. My name is Brad Edgeworth. I'm a double CCIE. I learned ISIS when I was doing my CCNP, and then definitely learned it when I was going after my route switch. I have worked in enterprise and service provider space, and I focus on operational simplicity. I love this protocol compared to the other link state protocol, and I'll just kind of leave it at that. I talk fast, so if you need me to slow down, some sort of ARM motivation will be good. I have about 120 slides I'm going to try to cram in 60 minutes. So to kind of get started with this, you've probably seen this before. There's an app that you can join into to get into a WebEx Teams room, or WebEx Spaces room. So if you have questions, I'll be happy to follow up with anything you might have on the topics we've discussed or anything else that might pop up in the back of your head. So go ahead and jump into that if you're not already added into that. And then the other thing is this is the agenda. So I'm going to provide a brief overview of the protocol. How many of you guys are using ISIS today? Can I get a show of hands? Okay, cool. How many of you guys know what you're doing in ISIS today? All right, so you're probably more relevant is going to be in the back half of this lecture when I talk about the area design. So the first portion of this is going to be around configuration, just to set expectations. So we're going to go through configuration. I'm going to show you on Nexus, iOS XR, as well as iOS XE. So I'll kind of point out this. How many of you guys are pure iOS XE in your environment? Pure iOS XE, all right. So for those that are hybrid, you'll probably want to follow some of the little tips I'll give you. So I like to start things off with a trivia question. So we have a packet that's going from R1 to R4. The question is how do we get the packet to flow across R5 while still allowing R2 to send directly to R3 from the loopbacks? So this is a little bit of a trivia question. Anybody think they might know the answer to start off with right now? Okay, hopefully at the end of the session you'll have a little bit more information to understand how this works. So to talk about the foundation of this protocol, it's a link state routing protocol just like OSPF is. However, when it was being developed, it was at the same time that OSPF was being developed, and it turned into kind of a political war of do you want DVD or do you want DivX to kind of give you a cross comparison, or is it VHS beta versus the other standard, which I can't think of off the top of my head. It does provide fast convergence. It's excellent for scalability. It's the reason one of the service providers use this a lot for connecting in their P2P or P2PE routers. And it also provides you a lot of flexibility as far as tuning. It was adopted in the ISO standardization, the guys who gave us the OSI model. Now, the fun thing is if you want to find the actual original spec for that, you have to pay money for it, which I think is funny. It's not actually an RFC, so just kind of bear in mind with that. The other thing is it gives you extreme flexibility. So kind of like how BGP and EIGRP allows you to have address families, we get the same functionality within that. So that is part of the reason why you're starting to see it in some of the other solutions like SD Access, you've seen it in OTV, et cetera, is because we have that flexibility. Now the other key thing to realize is it's a layer 2 protocol. It was originally designed as a layer 2 protocol. Now when Cisco got their hands on it, we said we're gonna make this layer 3 because we're only routing layer 3 protocols. So it's required to have IP addresses, but it's basically a layer 2 protocol to start off with. So kind of bear with that. We have 2 levels as far as the hierarchy goes, similar to how OSPF has 2 levels, but we do things a lot differently. So the first one is gonna be level 2, and that is our backbone. So the non-backbone is gonna be a level 1 area. So I've got a topology here, and you can see I've got some areas like 49.0.0.12, 49.0.3, and 49.0.45. So let me put some wrappers around this. The first thing that's gonna be different from what you might see from the other link state protocol is the area is based on the router itself. It's not on the interface. So a router belongs to a complete area. Now, with that also being said, we'll give some designation to the routers. So you'll see that I've now added a designation underneath the router of like L1, L2. That kind of gives you a designation as to what that function of the router is going to participate when it builds a topology. So that's something to kind of bear in mind. So when we talk about what the backbone comprises of, we'll have a layer 2 adjacency between L2 type routers. So there's our first L2 adjacency, and then there's our second L2 adjacency. So even though R1 and R2 are in the same area, they can still establish an L2 adjacency. Does that make sense? All right, same thing with R4 and R5. So they're gonna be formed within an area or formed outside of an area, inter-area, for lack of better terms. Now, with that being said, then we're gonna get into our level 1, which is the non-backbone areas. So those are going to form only between routers that are L1 of the same area type. So that's how we get our L1 adjacency, all right? So that's the basic topology with that. Good with this so far? All right. We're gonna keep rocking. So one of the things is you can actually have a router that's gonna participate as an L1 only router. So what we're gonna do is we're gonna flip R1 and R5 so that they are R1 only, or level 1 only. So they'll have that L1 adjacency to R2, and so R2 and R4 are going to provide a bridge mechanism to the other areas. Does that make sense? We'll dive deeper in how that mechanic works. Now, with that, there's no reason for R3 to act as an L1, L2 router because it's only connected to other areas. So we could tune it if we wanted to be only an L2 router. And so this gives us a little bit more of what our topology looks like. And so that kind of bears down, and R2 and R4 are gonna be L1, L2. So iOS XE, by default, the routers will come up as L1 and L2 routers to start with. And then you could tune them as you want to as well. In addition, I think I talked about this later on, you could also tune your interfaces that this interface will only form adjacencies at an L1 or L2 or L1, L2. So you can do a little bit more tuning in that way without impacting the relationship with other routers. So the function of the backbone is basically to take routes from other areas, as well as take routes that we have learned from the backbone, right, or other L1 areas, and carry it forward. So in this case, the backbone is gonna span across multiple areas. You can't do that with other link state protocols because there's only one area with that other link state protocol. This one, you have multiple areas that the backbone spans because it's a layer 2. That make sense? Question? Okay. So we talked about it being a layer 2 communication protocol. This is just some of the destination MAC addresses that we use with communication. So if you ever need to do like packet captures, these are gonna be the MAC addresses you're going to use. Because it's a layer 2 protocol, it does not work on IP-based tunnels. It doesn't work on DMVPN tunnels. It does work on GRE tunnels. So that's just something to bear in mind. So remember OTV? OTV worked off of GRE tunnels. That's how we got the magic to work. All right, so ISIS has 3 different types of packet types. We have the hello packets, which is used for discovery. And we also have link state packets, which is what we're going to use for sharing the database. So it might seem a lot like LSAs from the OSPF world. That's the LSPs. So just changing of some minor letter gets you the same structure. And then we have sequence number packets, or SNMPs, which is used to synchronize the link state packets when you have like a broadcast segment. And we'll kind of dive into that a little bit as well. So with that being said, the true magic of this protocol boils down to TLVs. Now, so the TLVs are basically modules or subcomponents that you can tack into the structure. And that's going to advertise different information as it passes along. So like the most important TLV to start with is TLV number 2, which is how we build out the topology. Building out the topology is key number 1. So TLV number 2 builds that out. Now, there's a numerical value assigned with that. And so if it has an unrecognizable TLV, it's just gonna skip that TLV and continue processing on to the next TLV. So, and TLVs do not get modified in transit. All right, so this is going to show you a little bit of a packet structure to kind of work with. You can see things like protocol description, which is down over here by the 08x3 that tells us it's running ISIS. We can see the header length. We can see PDU type. This is a L1 hello. So we'll have a hello for L1 level adjacencies, as well as a hello for L2 adjacencies. We can see version numbers and things like that that kind of correlate onto this. So that is where this is. Now, quick question. What does ISIS stand for? Should have started off with this earlier. Anybody want to take a guess?
Intermediate system to intermediate system.
That is correct. Intermediate system to intermediate system. And so there's actually, in the OSI model, a protocol for designated system, which is the host, to talk with intermediate systems. So this is just more or less router to router, not host to router. So that's where that comes from. So my apologies for not covering that earlier. So this is the packet structure, just to kind of dive into it. We'll go into a little bit more relevancy. So when we look at like a link state packet, this is where we actually are advertising network prefixes, we'll see things like the remaining lifetime. So it's 1200 seconds. So we'll do similar to how OSPF keeps a lifetime, so we'll have a constant flooding. The default value is set for 20 minutes. And we'll start counting down upon receipt, and when it gets to 0, we're gonna flush it. Now the advertising router is going to refresh the LSP after about 15 minutes. So there's about 5 minutes of overlap in case something's running slow in the network for it to kind of keep that network alive. So again, that's how we keep the packets live, is the countdown. The sequence number is just basically a way that we make sure that if there's a revision, like a network's added or removed, we can make sure that all the routers in that link state database have full-blown access to that. And then we have various attribute fields such as partition repair, attachment, and overload bit. We'll talk about attachment and overload bit in a minute. And then down here, you'll see where we have our network prefixes. So network prefixes can come in a variety of TLVs, depending upon whether we're running IPv4 or IPv6, or if we have narrow metrics or wide metrics. And I'll kind of cover this a little bit. Everybody doing good so far? Okay. I will make you stand up if I see people fall asleep. Just keep everybody active. We gotta be ready. We got a party to go to a little bit later on. All right, so, let me jump one. So here's a list of the common TLVs. I'm not gonna go through them just to kind of go through it, but the big thing here is 2 is what we build the topology off of. We'll use things like 22 for the wide metrics. We'll use things like 122 is the big one for the actual calculation of the metrics. It's not on here. And you'll see later on, we'll see things like IPv6 interface addresses along with reachability information. So we'll kind of dive into the specific TLVs as we get to it, but these are just common TLVs that you'll see. So within ISIS, we have 2 different network types. Not 4, but 2. Broadcast and point-to-point. And it basically boils down to this. Is it possible for more than one node to exist on a network segment? Right? So the default behavior is everything's gonna start off with broadcast, and when we have a broadcast, we're going to have a pseudonode, a virtual router, to help keep the LSPs in check so we don't have a lot of sessions to maintain. It's gonna help with the sequencing of the LSPs, similar to an OSPF designated router, okay? So pseudonode, virtual router, like I said, they were developed at the same time. So one of the things that was troubleshooting, or very troublesome for me when I was learning this protocol, is there's this net address. And if you go online, you'll see a variety of different ways you can do the net address. And it took a little bit of a while to figure out exactly what it was, reading the ISO spec and stuff like that. So I'm gonna break it down to what it boils down to. So basically we have the inner domain part, and that's gonna be the area at its shortest. Over on the domain specific part, that's the unique identification within an area. Make sense? Now, they didn't make things easy with the way they broke things down. So the inner domain part breaks into the authority and format identifier, which is like a regional, I'm gonna give you this specific starting point, and then it goes down to sub-organizations. So they set it so that you can cascade, kind of like you can have a root domain in DNS that can cascade to somebody else if you wanna sell off a subdomain to somebody else, et cetera, et cetera. Same thing with addressing in the global world with this. So then we have like the high order DSP, the domain specific part, an ID and a cell. The selector ID will kind of be pretty straightforward. All hosts should have 00 for a cell. And we'll talk about that a little bit later on. Now, diving a little bit deeper, oh yeah, that's where the fun part is. The high order DSP, that gets variable in length. So diving a little bit further, you can see where the area address and how it can be between 1 to 13 bytes. That's the biggest confusion when you look at the documentation because of the fact of you have that variable length. You know, how long is it? What is actually gonna work? The back half is the ID at 6 bytes with the 1 byte for the cell. And like I said, the cell's easy. It's 00. When you're configuring, it's always gonna be 00. Now, let's kind of walk through the logic. Don't read it from left to right, read it from right to left. So to start with, the cell, the final bits will always be 0. Kind of talked about that. The next thing is, the next 48 is gonna become like the router identifier. How do you make it unique? So some people will convert it to IP addresses. Some people just create 0001, 0001, 001, or 2, and they'll do a little bit of a tweak variation. The next 16 bits are basically gonna become part of your area. Like, what do you want for your area identifier to be? So that's kind of where it ties into, and then the other first bits is the AFI. So let me walk through some examples to kind of help break this down. So you could have a simple 8-byte area ID system ID. So we can see that the area is 07. The station ID is the 192.168.001.001, which looks like an IP address just with 3 digits for all your locations. See how that works? Makes it a little bit easier. You have to figure out a schematic that works for you. It's easy not just for you, but the guys that are answering the help desk. To show you, here's a 10-byte. Now, you'll notice that 49 for AFI, anything starts with 49 is in the private reserve space. You can go crazy after that, is the way that works. So 49, 1, 2, 3, 4, and then just whatever you want. That's a simple area ID right there. And then kind of breaking it down a little bit further, you can go full OSI NSAT format. Either one's gonna be okay. Now, you can actually have a router participate in multiple areas. So I think the default is 3 areas. So I could theoretically configure a router to run on that area, and that area as it does its calculations. You may not want to do that, might make it a little bit confusing from an operational standpoint, but if you ever have the need, you can do that, okay? Again, just because you can doesn't mean you should. And this goes back to say the cell is always 00 for that. So talking about the DIS. So this is a way that we kind of get over scalability issues of maintaining that session state between the routers is we create that pseudo node. And so what that does is that allows us to synchronize the process. Now, what's gonna end up happening is we're going to have a link state LSP database for all of our areas. So everything that's in the same area L1 is gonna have that same LSP database. The same thing is gonna hold true for all those devices that are in level 2 will have the same LSP database for 2. So to keep that same logic, we're gonna have a DIS for level 1 as well as one for level 2, okay? And so this helps with the synchronization. So one of the things you can do to optimize your network is if you've got a simple point-to-point using Ethernet, just convert it to point-to-point so you don't have to maintain that DIS. And I believe we'll get into the synchronization process within that. So what happens is if a router joins and it notices that I don't have the latest revision, he'll send out a CSNP packet which says, I need a refresh of the database. Now that packet goes to everybody because it's a layer 2 protocol. It's gonna get broadcasted to everything. But the router that is running the DIS role for that will then start to send out the appropriate LSPs that are missing to bring them up to the most current revision. And that is a broadcast as well from a layer 2 perspective. So all the other routers will get it too in case there was something missed. So that's the benefit of the DIS. We good with that? Am I moving too fast? Need to slow down? Okay. All right, so IS-IS configuration. So we got a simple topology. We got an iOS XE box for R1, XR2, and Nexus. How are my XR guys? Got a handful of extra guys. My Nexus guys. All right, everybody else is representing iOS XE, and then some. All right, so the way the configuration is for iOS XE is it's router ISS. Now notice the process ID is optional. It's not optional on Nexus, and it's not optional on XR. If you want to make things consistent for your environment, the way I would do my network is I would put a process ID that matches the name that I put on my XR and Nexus boxes. That way my level 1 guys don't have to figure out what's going on. Because the other thing is I've seen sometimes, you'll notice as we get down to the bottom after we configure the logging, which isn't enabled by default, we identify our net, is we go underneath the interface and we'll do things like IP router ISIS. So if you get used to the mindset of putting that process ID on there, not just when you're configuring the protocol, but the interface, you'll have it link up. I've seen a lot of different configurations where they'll define it in the process ID, but they won't put it on the interface, or they won't define a process ID on that, but they'll put it down on that, which puts it as 2 separate ISIS protocols on that box. Make sense? So that's a thing to look for as far as if you're doing a deployment configuration. If you're doing existing deployments, maybe that's something you want to go back and clean up just to make life simpler for your operational guys. And if you're running iOS XE today and you're doing a new deployment, start doing it now because you never know when you're going to put Nexus or XR in your network. All right. And then here's the cool thing. Enabling IPv6 is like putting IPv6 router ISS to process. This is one of the best things I like about this protocol is similar to EIGRP, it doesn't take a lot to actually add in IPv6, assuming you're using name mode. Same thing goes true with this, versus if you're running that other link state protocol, you gotta start up a whole other process and then figure out how you're gonna convert it over that, and then also enable IPv4 too, which the other protocol does do both, but it requires IPv6. So going through this, here's the configuration. Again, the key thing I want to point out is about the middle of the screen where the green dot's at. It's underneath the interface for gig 02, IP router, ISIS, Cisco Live. And capitalization does matter, and then you can see where I put it under gig 03. And then you can see my net, I kept it simple. I just did the 49 for the private addressing. My area in this case is 0123, and then this is just identified as 001.001.001. That's my new unique area ID. And then my cell is always 00. All right, so for XR, one of the things that I don't like about this is part of your configuration resides in the process, part of it's underneath the interface, so you might be doing some scrolling. I'm an XR fan. Everything goes underneath the XR family. I love this operating system. If you want to log adjacencies, you got to put the command in there, define your net, and then if you're going to run IPv6, you have to initialize the address family because it's not initialized by default. And then underneath it, you go into your appropriate interface, and then you identify what routing protocol, what protocol you want to run under there. If it's IPv4 or IPv6, just to kind of hit on that. And so there's IPv6 where we turn it up on both. So there's our configuration. You'll notice that it kind of gets into like a little hierarchical within the parentheses. So there we define our net. Now notice in our area identifier, we did 002 to match R2, right? So that's how we're gonna identify each buddy differently. And then again, underneath the interface, it is where it's configured. So we have that hierarchical stance, 2-stage commit. So we hit commit there and it processes. So that's XR. All right, NXOS. First thing you gotta do, turn the feature on. Can't do anything, turn the feature on with Nexus. Router ISIS, process ID, log adjacency. You would think that they would start making that kind of default. I don't write the code, I wish I did. Define the net address, and then enable ISIS underneath the interface with either IPv4 or IPv6. Pretty straightforward. So this is the configuration. Again, you'll kind of see where it jumps from a process configuration to underneath the interface as far as how that works. But then you'll start to see the neighborship for the adjacencies. And that's why I like to enable the logging adjacency changes so you can see when it comes up or down. The other key thing that I didn't point out is notice there's an adjacency being formed for L1. That's the first notice. And then there's one for L2. So for each level, it's being identified. All right, so back to our trivia question. So we got the scenario where we're trying to get traffic to flow between R1 to R4, take R5. Oh, I guess we're just waiting for, there we go. There's the pack between R2 and R3, so a different pack. Anybody want to take a stab what's going on? Okay, you'll get the answer soon. It takes one command on 4 routers to make this happen. And I'll give you a hint, it doesn't involve R5. All right, so how do we identify that we have that neighborship? We've done the configuration, we've got a log message, but it's been days or weeks since that's happened. How do we make sure things are still going to be up and online? So with that, with R1, we have show ISIS neighbors. Now, ironically, on iOS XE-based platforms, you can still run the show CLNS commands for various outputs and interface stuff, even though we're putting this over IP. So that's an interesting aspect. We'll see the system ID kind of pulls through. Now that's showing a host name there, and it's showing our type, level 1, level 2, the interface and the IP address, as well as the hold time, and a circuit ID. So that circuit ID is coming from the neighbor that we have that adjacency established with. And then just to kind of show you the same thing, one of the questions I have is, how do we get the actual router name? Is that coming from things like DNS? Is that something else? Anybody want to take a gander? What? A TLV, is that what you said? LSP, yes, inside the LSP, that is correct. So there is TLV 137. So let me just kind of throw this. TLV 137. So inside the packet, you'll have the host name. It identifies topology. I know that other link state protocol, you can use DNS to look it up, but you know what? Sometimes DNS is not wrong. This is actually in the payload. And I've had some cases I worked where that TLV was not being advertised. They're like, my routing table is compromised. It's like, no, you're good. Just the router forgot to add it to the TLV. It was a bug. So everything was stable. So that's the kind of cool thing. How many people like to work off of router IDs or like to work off of host names? Host names, raise your hand. Router IDs, don't raise your hand. All right, so that's just something kind of, I think it's fine when I'm troubleshooting to find things quickly and easily by host name. I don't memorize IP addresses because I get dyslexic, which is very bad. Very bad for a network engineer to be dyslexic with numbers. All right, now with that being said, you can disable that if you want to. So on iOS, XE, and NXOS, you just do no host name dynamic, and then on XR, host name dynamic disable. And then you'll go back and you'll see the system ID. So that's where hopefully you've got a good system ID with that area as far as what that works. So that's your other alternative. Me personally, I like having the host name in there. All right, so continuing on along, show ISIS neighbors for XE, we'll see all that fun stuff. Back to XR, it's the same thing. Now notice you'll see the SNMPA, which is just the fancy word for like the MAC address. You'll see the state, the hold time, and the capability. So with XR, it combines them what your adjacency is, versus iOS XE is going to give you a line for each individual entry. So that's a little bit of a difference as far as how it works. Then when we look at Nexus, same thing for the most part, SMP ID, the level 1, level 2, so it kind of mimics a little bit of XR and a little bit of iOS XE for the duplicate lines. That's the commands we'll use for verification. Kind of going along with this, what is required for adjacency? So the interface has to be active, has to share a common subnet. The protocols must match per topology. We'll get into topologies because you can run multiple different topologies for IPv4 from IPv6. But if you're running the single topology and one is configured with IPv4 and the other one's IPv4 and IPv6, no dice. It's not coming up. So generally, I like running multi-topology where possible because it gives you the option of doing IPv6 later when you're ready to do that. How many of you guys are running IPv6? Can I get a show of hands? Who's running IPv6? So that's what, 15% maybe? Okay. If you're not, you should start thinking about it. If you're a large company and you got acquisitions, those can complicate factors. All right, so going back to this, circuit types have to match. So either going to be a general, which is the broadcast, or point-to-point to get adjacency. Going along with that, the router level areas have to match. Now remember, we're going to form an adjacency on an L1 perspective and an L2 perspective. So if this router is L1 only and this router is L2 only, they're not going to form. If this one's level 1 and this one's a level 1, level 2, we'll form adjacency only on the level 1, not the level 2. Okay? The other thing is for L1 adjacencies, the area address has to match. We have to be in the same area in order to match. And then the other thing with that is the system ID must be unique if they're in the same area address. So you can't have, 49.0001, 0001, 0001.00 be on 2 routers in the same area. It no worky. If you got authentication, that has to be turned on. And then the other thing is MTU matches. The reason the MTU matches is because we actually pad the hellos when we're doing neighbor detection. So we want to make sure if we're going to pass routes, we aren't going to have problems with this interface being an MTU of 9,000 and this one at 1,000, or this one at 1,000 and this one's at 1520. Now, there is a command you could do to disable the MTU padding to bring up an adjacency. Be very careful if you use it. It's there. Works great in the right design. In a bad design, yeah, I'll see you at 3 a.m. But that's kind of where that boils down to. Any questions on this? Okay. All right, so let's talk about the topology constructs and how it kind of is built together. So right now, taking back to our topology where R1 through R5 are all L1 and L2 routers, and we got 3 areas. Like I said before, they're going to maintain a copy of the LSPs in a database for a level. So how many topologies do you guys see in this diagram? You see 3. How many see 6? Raise your hands if you see 6. How many see your hands if you see 3? How many see double for the beer? All right, so there is actually 3 topologies within this diagram. So let me just kind of break down what that looks like. So with this, the backbone is a single topology. And then we're going to have another topology over in area 49012. There we go. And then we're going to have another topology over there. So that's how we get our 3 topologies. So in this context, R1 and R2 are going to have a LSP database for topology 2 and an LSP database for topology 1. And then the same thing for R4 and R5 for topology 3. R3 is only going to have topology 1 link state protocol database. So that's kind of how that works. And all routers will have a full, complete copy of the LSPDB when it does its calculations for the shortest path first tree. All right, so this is one of the cool commands that I love about this protocol is you can do a show IIS topology, and that's going to show you your routers either within your level 1. So let me just kind of bring this out. This shows me my topology. This is running R1. What's in my level 1? R1 and R2. That's it. But remember, it's also got another topology for the level 2, and it builds that out. And within that, you'll see the metric and what the next hop is. So this gives you a router by router view. So something that is different about how we calculate and do things for convergence is we function off of building a topology and we stack the subnets on top of it. So if we have to reconverge, we're reconverging the topology, not all the routes. The routes will follow because it's a reference link on the topology. Does that make sense? That's one of the things that I think makes this protocol converge faster. I could be biased. Versus other protocols where if you do a change in the network, well, guess what? That's how they build their topology is based off that network, and you're just going to recompute everything. So that's how you do that. So this is iOS XE. The same thing if we want to look at XR, show ISIS topology. The commands are consistent, which is great. You'll also see things like SNMPA, so this case is point-to-point. It will identify if it's point-to-point or if there's a dis in there. And then here's Nexus. I didn't draw the cute little boxes around this one, but you can see here's topology 1, and then down at the bottom is the level 2 topology. So you kind of build that out. This is the key thing. When I'm doing my first level of troubleshooting, if I got all my routers are populating and I have metrics, that's a good solid foundational. I've checked that box, and now I'm moving on to further my troubleshooting process. If I have problems here, I need to figure out why I have problems here before I move on. So if I got metrics and I got my routers, I'm good. I'm moving forward. So moving on, oh, there's my boxes, sorry. All right, so how do we optimize an area? So if we think about how R1 is gonna get connectivity to R5, we got our 3 topologies, let's look at how the LSP is advertised through the domain. So if we go back to, here's our adjacency, kind of like we had before, what's gonna end up happening is, oh, I guess I lost my animation. So the routes come across as 128 for narrow and 135 for the wide. And so that's how we have the capability going forward for this. This is the adjacency. Sorry, I got ahead of myself. So if you want to tune your adjacency without modifying your router level, you could do it on the interface level. So in this case, if this router R1 was still a default L1, L2, I could just modify that interface itself to be an L1 only, and that's going to make it, in essence, be an L1. Does that make sense? So the way I do that is I go underneath the interface, and I'd say IS type level 1 or level 2, or I'm sorry, level 1-2 or level 2 only. And you can kind of see what it is for NXOS. So that's kind of where you do your router levels as far as changing that. And then your interfaces, sorry, I got it confused. Top is the router level where you do the configuration, and down on the bottom is your interface-based commands. And remember, XR, everything's gonna be within that process in the hierarchical format. That makes sense? Sorry, I got it out of order a little bit. All right, so if we view the topology from R1, it's a lot smaller. And then if we look at R2, we'll see that R2 has both a level 1 and a level 2 topology, which is expected based off of what we've done with the configuration. So R1's basically not going to be present in the L2 topology database because it doesn't exist, because we changed that connection. So how do we build the topology? So we kind of talked about that. The topology is being built on the ISIS, the TLV number 2. That's the one I told you was the most critical. So what happens is the LSP IDs that are not 00 are going to represent, the DIS. So remember when we told you we did the configuration, everything's gonna end as 00? That's how we know what the routers are, and everything that's not a 00 is gonna be a DIS, because if you have a router that is connected to 4 or 5 broadcast segments, and it is the DIS for all 4, you'll see a uniqueness within this, and I'll kind of dive into this for you. So here's our topology here, so R1 to R2, that's a point-to-point, and then R2 to R4, R3. So what I want to do is in the R1 to R2 link, you can see that the LSP ID, where it's kind of going with the show ISIS database. And so this is going to show you things like the sequence number, the LSP hold time, the attach bit, the overload bit, things along that nature. So if we dive further and we look at the detailed state of that, what we'll start to see is things like where it's connected. So we can see that R1, 00, what it's actually going to be attached to, and we can see the metric is 10, but it's attached to R2. So that's where it's building that topology, is based off of what it's attached to. And then this is where we list in the IP addresses that are coming across with that topology of what R1 holds. Does that make sense? So that is what boils down to that. And then so what we're gonna do is, if we exclude this, we can see the ISR2 kind of basically points to the fact of is R1. So I did a detail, I didn't filter it this time, but all we're just looking at is R1 says that his neighbor is R2, and R2 says his neighbor is R1, and that's how it merges. the topology. All right, so that gives us the point-to-point link. Now let's go on and let's talk about the broadcast. All right. So multi-topology. So now we're going to add in this broadcast of R2, R4, and R3, and let's look at what that looks like. So we're just going to focus in on that. And now with that, we're going to run the same show ISIS database detail. And you'll notice we'll see things like R200, R300, R400. But notice that, R4.01, that's not a host. That's the DIS, the DIS. So let me just go through and show you what this correlates to. So we put our router topology, we draw some connections. So R2 points to R2, R3 to R3, R4 to R4. Well, what does that actually reflect to, right? What are they connecting into? So what I'm going to do is I'm going to change out the connection of R4, the 0, 1. It tells us, that's the DIS for that segment. It tells us what you're actually physically connecting into. So you can inversely say that that DIS is attached to that. Now you could tell who owns the DIS because of what's in front of it. So if the DIS was to change to like R1, it'd be R1.01 or 02 or 03, depending upon what was available on that router. And so if we go back and map that, oh, there we go. There's the virtualized DIS because R401 must be the DIS that connects the joints, the pieces. So that's how the topology is built. Questions? Okay. All right. So kind of continue along with this process. If we look at the actual interface, because I took out some of the filtering, so R2 says it's connected to R401. That's the virtual connection. So again, I'm just releasing a little bit different output of what you're looking at the detailed database, but that's pointing to the DIS. And then if we actually look at R3, R3 says it's connected to R401, which again is the DIS. And then if we look at R4, even though it is the DIS, he's still connecting to the virtualized pseudonode of R4 for the DIS. So that's how you look at it. Again, I just kind of walked us through the process of how you get there without kind of overloading with CLI output. All right. So let's go through and you can start to see where the interfaces are connected. Now here's the cool thing. Notice that the metric on the DIS all shows 0, but you have the actual count of 10 to get to the DIS. So that's just an interesting way when you think about how the path calculation, because otherwise if there was a metric on there, you're double counting for that connectivity. So that's the kind of a cool thing is the DIS will have the metric of 0. All right, route advertisements. Let's dive into how this works. So going back to our topology where R1's L1 and R2's L1, L2 and R4's L1, L2, let's talk about how the routes get across. So when we look at R1, we look at the database for level 1, you'll see things like we're only really seeing the basic area address of 49.012, the metrics R1, and the IP addresses that are associated to it. So how does that actually come about? So the metric for the topology is identified down here on this column, and then we'll start to pick up on other things that kind of correlate as far as what are the connected IPv4 networks. Because remember I told you that we build the topology first, and the networks get stacked on top. That's exactly what's happening. And then if we had IPv6 addresses, you could see that tied in. That's going to come through a different TLV. So we look at the route advertisement of R1's loopback. It's going to come across as a L1 LSP. It's going to make its way to R2. The job of a L1 L2 router is to take that L1 LSP and push it into the L2 topology. So that's exactly what's going to happen. So it's going to take that L1 route and place it into the L2 database. So now it's went from green to blue, and that's going to get cascaded to R3, and that's going to go advertised to R4. So the question I have is how does R5 get the route? Does R4 take that route and now make it L1 so it's reachable? And the answer is no, it doesn't. So this is where the conservation actually happens. So part of what actually is going to happen is when R4 is the barrier, the entry point, the translator between your L1, L2, is it's going to add what is known as an attachment bit. And so the attachment bit is basically a way of identifying it as a gateway router. It's going to advertise a default route in lieu of that. So the only thing that's going to be advertised is that. Does that make sense? We'll talk about this a little bit more when we get into some of more of the design stuff. All right, so the attach bits for that. So we're moving forward. You can see the attach bit when we look at the database. There's the attach bit right there. Cranking right along, you could look at it from an explicit view right there underneath the attach bit. And so that's how that's built out. Notice how it comes in as an L1 with the default route. That's how it's seen on the router itself. All right. I'm running a little bit behind, so I'm gonna try to pick it up. But the other key thing is notice when we look at the backbone routing table, everything looks business as usual. You will see even on R2, the loopback is an L1 route. It's not an L2 route. There we go. All right, so overload bit. So typical traffic flow, if we look at the pass through XR2, it's 10 plus 10 is 20. The bottom is 10 plus 10 is 20. Through it's 30. So normal routing is going to go through towards R4, I mean through XR2 or R5. But there's times where you want to manipulate traffic flow or things like that. So this is where the overload bit comes into play. It was originally built for when a router was overloaded, and how do you signify you can't take any more traffic? That's where it kind of came from. And that's basically what that overload bit is used for, and traffic will not flow through a router that has the overload bit set. So that's kind of what happens. It's in the LSP advertisement. This talks about typically it was when memory exhaustion occurred, but most doesn't happen in today's routing platforms. There's more than enough routing memory in that. So you could set it to have it where you want to take a router out of maintenance. You just set the overload bit. It's going to redirect traffic around it. Or for my service provider friends, while you're waiting for BGP to come up for the initialization, you might have it set for the overload bit's going to be in place for 2 to 3 minutes while you wait for your BGP table to establish and fully initialize. So that's kind of where that is. So when you have the overload bit, we basically set it on XR2 and R5, and now traffic's taking the longer path, even though that's not the most optimal path. And you can see the overload bit when you look at the database on the last column. The overload bit is indicated right there. All right. So route metrics. So this is the SPF tree. The short rendition is you got the topology on the left. The tree will look different based on the router calculating it. That is how it built it. It's not the actual complete topology. It's just what it's forwarding off of at that point in time. And then so interface metrics, TLV 128 is narrow metrics. It doesn't really give you enough speed to get full granularity. So what ended up happening was the default standard is set for all your interfaces are going to come up on 10. So all your interfaces are set for 10, so you might need to manually tweak that. Now there is an exception to this rule, and that basically boils down to the fact of there's the 10, and it's on the next slide I talk about it. But they are statically set as far as that value. Now the difference with that is Nexus. Nexus sets the value on a reference bandwidth of 40. So something just to kind of bear in mind. Same thing with OSPF and some other protocols, right? They're like, hey, we're a multi-gigabit platform. So you might want to think about what that is. How do you build that number reference for your slower serial links? If you've got faster 10 gig, if you've only got a range of like a small route to go through between 1 and 63 for statically defining it. So what that came up with was interface wide metrics. And so this now allows you 32-bit values, and it does not impact the way the topology is built. Topology is built on type 2. So this is the cross compatibility. Now what you can do is, you notice how now the topology, the metrics are off. Topology's present, metrics are off. The reason for that is because the other routers are using a different type of metric than what you're using. So this is where you start to investigate, well, what are my metrics, okay? So what we would do in this case is, talks about the TLVs being transmitted as long as they're recognized. So TLV 135, which is wide, but when it hits over, it gets dropped. It's not gonna process. So this is where TLV 128 carries forward. So what you're able to kind of do is you can see narrow metrics by default on XE and XR, where NXOS uses wide metrics by default. So you could see this with the show ISS protocol. You could see for iOS 6e, the wide metrics are set for none for both your L1 and L2. XR, you see the same thing, narrow and narrow, whereas NXOS it's going to advertise wide, but accept narrow and wide. So just a little bit of a different behavior. So you could set it to where you could use narrow only, wide only, or transition, which is both. So this is what you'd want to do if you've got half mix. Start with transition, get everything on transition, and then convert to wide. And there's the command you'd use, metric style, narrow, transition, wide. You can see the appropriate style it's going to go into. Note, NXOS only really allows transition. All right, so back to this trivia question. You're going to have one command on R1, one command on R4. We'll get back to that. IPv6 support. So IPv6 basically comes across in TLV 236 for the reachability and 232. That's kind of the high level for it. One of the things that you'll see is we have the capability of having multiple topologies. This is where I said if you have the same topology, you have to have the same protocols to get that connection to go across. So what I recommend is if you're starting off with a new deployment, just go ahead and put yourself a multi-topology in case you're going to potentially do IPv6 later, which hopefully you will. There is a transition mechanism for that as well, if you wanted to kind of go through that process of evolution. So there's your updated packets, mismatch, kind of the same thing. All right, so single topology, there's no planned differences. So basically that means if you're not going to manipulate your traffic flows between IPv4 and IPv6, all your routing is going to be exactly the same, you can run single topology. If you think you might want some IPv4 traffic to go this way and some IPv6 to go this way different, then that's where the multi-topology comes into, different route manipulation. Think of it like if you're a spanning tree and you use MST, same kind of concept to a certain degree. All right. As said before, you could use this transition, which will allow you to have the best of both worlds. All right, that's the basic. And then wide metrics is going to be required to go in this multiple topology, or you could be in transition style. All right. I want to get into some of the design stuff. All right, so anybody want to take a guess what the answer is for the trivia question? So what we're going to do is basically we're going to make L1, L2 link between those two routers, and then we're going to make R1 and R4 L2 only. So that's how we manipulate the traffic flow. So if you want to make some money at the bar, talk somebody up about ISIS. Yeah, I'm an SP, I'm an IS expert. There's a good chance you could take some money off the table off that one. So, all right, so more to design. So R1 needs to send packets to R8. So R1's L1, it's going to forward to R3 or R2, but it's going to end up at R4 and make its way to R8. Okay, looks good from a solution standpoint. Let's swallow the green ball and figure out what happens. So what happens is when it gets to R5, at this point, R5 is L1. Does not know how to get to R8. The only way it knows is the attach bit, and the closest for that is R4, not R7. So now what's going to end up happening is it's going to ping pong back and forth, and now you have a routing loop. So this gets into the design of how you want to do this. So basically, if you're having an area be transition, all routers need to participate in L2 for that connectivity. There's a little bit of ways you can do things differently, but that's kind of something to bear in mind. So that just talks about being continuous for the process. All right, so suboptimal routing. So we fixed it. R5 now is L1, L2. So R1 needs to send packets to R8. Well, which way is the most optimal path for it to take? So it's L1 only. It's going to go through the shortest path to get to the attached bit, which is 10 versus 20. You would think the path through R3 to R7 would be faster, but because it's shorter distance to get to the attached bit, it's actually going to forward across the longer path. So just something to be kind of aware of with the design aspects of this. If the metric was, the question was, if the metric was the same, it's a hash. which one you get to. So there's a way we can solve this. I got 5 minutes left, so I'm gonna try to cram through this. But the way you do this is you could actually leak more explicit L2 routes into an L1. So there's a command you can do to leak those more explicit routes. So for my service provider friends, that's probably gonna be your PE loopback interfaces, because that's what you're using for MPLS to get the connectivity. So in this case, we're on XE, redistribute ISS IP level 2 into level 1, and then on XR, propagate level 2 into level 1, and then Nexus is distribute level 2 into level 1 all. Now, if you want to, you can do conditional and tie it to a route map or RPL to be selective on which routes you want to do. And if you have that more explicit route, that's how you're going to overcome the suboptimal routing. All right. So area and scaling. So this is going to get more into the POP design. So you can have more than 400 routers in a backbone as possible, because remember, you can span it across multiple different areas. Along with this, starting with L2 only everywhere, it's a good choice, because backbone's going to exist everywhere for the most part. And then that also allows you to have future implementations of level 1 areas later on. And then basically use areas where suboptimal routing could be acceptable, depending upon what the size is. Like a campus might be a good place for that. So this area design is L1 POP only. Basically, it's flat. It's perfect. You don't have problems if you're doing things like MPLS TE for traffic engineering and things like that. All the routers in the same area, again, 4901. The downfall with this is, it's L1 only. All right. The other thing is SPF computations in one area will cascade into other areas. So just kind of a thing to bear in mind. So the next thing is an L2 only POP. Let me just go and build out the slide. With this, we make everything L2, but we keep the area ID the exact same. This is going to give you the same functionality with TE and things like that. No restrictions. And the other thing was, go here, it allows you, if you want to converge later into the second one, which is L2 only with different areas. So here, you could change this into where you've got different areas on the edges, so your core still stays the same. Now, when you do this, your TE, if you're an MPLS guy, is gonna get a little bit more fancier to deal with. It's nothing major. And you don't have to deal with summarization or route leaking or things like that. So all routers in L2 share the same convergence. And then the cool thing about this design is 1901, the 4902, 4904, and add that into an L1, L2, and make the sub-routers L1 only. So that's gonna be this next thing right here, where we'll see that we actually make L1 exist in that area, in the 4902 on the outer edge, but the ones that connect us in the backbone are L1, L2. So you don't have to really worry about the inside routers converging. So that's good for like campus networks or things like that, or area POPs for my service provider folks. So that's pretty much basically it. And then, it keeps your SPF computations down because you won't have a lot of impact typically in your backbone core networks. And then this kind of dives into, if you have L1, this goes the same thing with the connectivity to the core. You have a chance of going to the router on the left or the router on the right. You could have that suboptimal routing that I showed you earlier with that diagram, to overcome that, that's where route leaking is gonna come into play to kind of fix things up for you. And then you can also do summarization as well if you wanted to, if you do a route leaking with summarization. L1, L2. The other thing, this just talks about the BGP next hops for my provider friends. Typically that's your loopback interfaces. So that's kind of where that comes into. And then it also gives you optimal inner area routing for that. Metric style wide is configured with leaking for that's your MPLS VPNs. What other fun stuff? L1, L2 at the POP, we talked about that. XHops, that's pretty much it. So that's the end of the session. I hope you guys found this useful. Fill out your surveys on this. What is it, 100 points, you get a free pair of socks, because we could all use a pair of socks. I hope you found this educational. I will buy everybody a beer later on tonight. I'll be the one with the fancy hat. And when you do your survey scores, just bear in mind it's about the content, the presentation, not the room or the temperature, what you guys had for lunch. Although, the beef souvlaki was actually halfway decent. With that being said, I hope you have your time. I'll be up for any questions you guys have. And there also is the WebEx room as well for other questions. Thank you.